So this is a nice report or a review paper to follow up with after the Arctic prog, or what was it called, Arctic vital signs report, health of the Arctic, whatever Noah called it, that we looked at the key indicators, vital signs of the Arctic during 2024. Basically, it goes from October 2023 to September 2024. That's the water year, as they call it. This paper is a review paper, which means it's very long and it has an incredible number of excellent references. And I'm going to just take the figures, which are very instructive or useful in learning what the main messages are. And I will be brief as usual, but you can follow up if you are interested in the details. So the title is Process Drivers, Intermodal Spread and the Path Forward, a review of amplified Arctic warming. Basically, we know that the Arctic is warming much more rapidly than any other part of the planet, and Middle East and the Mediterranean are giving it a run for its money, but sea ice loss and so on. And we've casually mentioned ice albedo feedbacks, cloud water vapor feedbacks, and so on for the Arctic warming. What exactly are the processes? Obviously, there are many studies which have looked at it, and they all emphasize different aspects, which means there is no one answer. It's not one process, obviously. So what are the key processes that are likely involved, and how are the models doing? The news is mixed over there, but models do Arctic amplification, so we'll see overall how they are doing. And there are various key feedbacks that we'll look at. Let's start by reading the abstract. Arctic amplification is a coupled atmosphere sea ice ocean process. Land should be there as well. This understanding has evolved from the early concept of AA, Arctic amplification, as a consequence of snow ice line progressions, though more than a century of research that has clarified the relevant processes and driving mechanisms of AA. The predictions made by early modeling studies, namely the fall-winter maximum bottom-heavy structure, the prominence of surface albedo feedback, and the importance of stable stratification, have withstood the scrutiny of multi-decadal observations and more complex models. There is a digger that's going, what is the word for that? I forgot. But earth mover, I guess, makes a lot of noise. Yet the uncertainty in Arctic climate projections is larger than in any other region of the planet, making the assessment of high impact near-term regional changes difficult or impossible. Reducing this large spread in Arctic climate projections requires a quantitative process understanding. This manuscript aims to build such an understanding by synthesizing current knowledge of AA and to produce a set of recommendations to guide future research. It briefly reviews the history of AA science, summarizes observed Arctic changes, discusses modeling approaches and feedback diagnostics. We'll look at a table and assesses the current understanding of the most relevant feedbacks to AA: ice albedo feedback, temperature feedback, ocean transport, heat transport, atmospheric heat transport, all those good things. These sections culminate in a conceptual model of the fundamental physical mechanisms causing AA and a collection of recommendations to accelerate progress towards reduced uncertainty in Arctic climate projections. I won't read the recommendations, but basically they focus on the need for more observations, but also diagnostics of the feedbacks, because we don't know what is amplifying the which feedbacks are amplifying and which are damping the warming, and net result is still the amplification, of course, and so on. Our conceptual model highlights the need to account for local feedback and remote process interactions within the context of the annual cycle to constrain projected AA. So we know that Rossby waves come from the tropics, heat waves are coming in, so there is remote forcing, and then there are local feedbacks which are very critical, which we will look at more predominantly here. We recommend raising the priority of the Arctic climate sensitivity research, improving the accuracy of Arctic surface energy budget observations, rethinking climate feedback definitions, coordinating new model experiments and intercomparisons, and further investigating the role of episodic variability in AA. This is not well captured by the models, and we need to understand this episodic nature better. It's not just warming all the time, it's having these ups and downs. And Arctic warming is very critical because it's arguably now clear that the jet stream depends on this Arctic warming, and jet stream meanders are causing all kinds of extreme events all the way down into the monsoon region in the tropics, right? So let's run through a few figures. Here is the Arctic amplification. Essentially, you see the warming here. This is for 1960 to 2020 in kelvins per decade surface temperature trend, and you can see the zonal mean temperature trend again in kelvins per decade, and this is going from the South Pole to the North Pole, and the Arctic jumps out really clearly, right? If you do the zonal mean meridional section of the warming trend for the period of 1960 to 2020, then Arctic amplification is very, very prominent as a whole. This is looking at different periods, 2002 to 2020 surface temperature trend, 2000 to 2020 surface air temperature trend. This is the TS minus TA trend. So how is the atmosphere warming and what the surface is doing? So TS minus TA is mostly negative here. These are largely positive in terms of surface temperature trend, except down into the Greenland, North Atlantic, Labrador Sea region. And here also you see surface air temperature is also similarly negative, but if you look at the difference, that tells a slightly different story. And this is the IC trend, which is again I keep forgetting the sea ice concentration. So that is the ice concentration trend. So there are obviously largely negative trends, except here a little bit of zero or slightly positive trend down in the Labrador Sea to the west of Greenland. The regional trends we saw even in 2024, or the overall trends in various factors, sea ice extent, snow cover extent, and so on, also showed regional local trends for the Eurasian versus North American parts of the Arctic, right? You expect the meanders of the jet stream, land distribution, everything else, land use and so on, to have an impact on local feedbacks and regional trends. So this is the Arctic surface warming seasonally. So we are looking at December, January, February, in March, April, May, and June, July, August, and SON. So the maximum warming is from fall into winter months, reduces into spring and summer. Obviously tells you, you can see that here as well. So if you go from the South Pole to the North Pole, again you see the seasonality very clearly here, winter standing out. And it's not unusual just in terms of the circulation, the polar vortex, and everything that happens in polar regions in the winter. And the equator to pole temperature gradient is the strongest, the energy transport is the strongest, and the jet stream is the strongest, and so storm track is the strongest. So you expect winter to have a special meaning, even in terms of its response to global warming. Okay, I'm being very brief. You have to go and read the details, obviously. Here we are looking at atmospheric distribution. So again, going from South Pole to North Pole, and this is the ERA 5 temperature trend. Obviously, we said it's bottom heavy, which means warming is very amplified near the surface, but it is amplified all the way into the upper atmosphere as well. Let's not worry about the stratosphere, but you can see how different it is in the zonal mean air temperature in terms of the tropics and southern ocean and Antarctica versus the Arctic amplification. So just keep that in mind, that there are many special processes happening here, remote forcing and local feedbacks, that are creating this Arctic amplification. So these are the recent changes in the Arctic surface energy budget. So you want to understand what is causing the warming in terms of just top of the atmosphere energy, which is very critical for explaining the patterns and the overall warming trend itself. So you're looking at Ceres, which is the satellite-based energy budget calculation. So this is annual Ceres surface radiative flux trends in watts per meter squared per decade. And this is again different components of the heat fluxes. So recent changes in the Arctic energy budget: linear annual mean trend from 2002 to 2020 for surface, downwelling long wave radiation, upwelling long wave radiation. So atmosphere sends down something, surface sends back something. Downwelling short wave radiation and upwelling short wave radiation, so albedo impact, and sensible heat and latent heat as well. Okay, so you can see that sensible heat here is much larger than the latent heat in terms of the trend, and that corresponds to the differences in the surface and air temperature that we are looking at, right? Sensible trend is directly related to the difference between the surface and the air. That's what drives the sensible heat. Latent heat flux is related to evaporation and so on, right? Well, not and so on. Precipitation can also have an impact, which is critical in these latitudes compared to lower latitudes. Okay, radiation data is taken from Ceres, and sensible and latent heat fluxes are derived from airs. You have to be careful, because this is Lynn Boyce's work from NASA Goddard, which was a student that worked with me in the beginning. I hope she's happy. She's doing well. Anyway, when you derive fluxes, closing the energy budget is tricky, because sensible heat flux will have temperatures, wind speeds, exchange coefficients, and latent heat flux has humidities, temperature dependent humidities, saturation humidity, specific humidity, wind speeds, etc., and coefficients. So it's not necessary that the budgets close, but sometimes you tweak it, you adjust it, and so on and so forth. So you have to be very careful when you do energy budgets with bulk formulae derived fluxes. They are not directly measured, other than long wave radiation and short wave radiation. So that's always something to remember. What are the models doing? Obviously models have a large spread. I won't even bother with it, but this is the future scenario, SSP 5 8.5 air temperature trend. So you can see news is not going to be good. We are going to warm the upper atmosphere. In low latitudes we will begin to see Arctic polar amplification even in the south. This is for you have to be sure which period we are looking at. Arctic amplification in CMIP 6, zonal mean temperature trends for the 2022 CMIP 22 CMIP 6 models from the SSP 5 8.5 simulation. Inset depicts the seasonal cycle of temperature trends for the Arctic domain. That's poleward of 60 north. B is the vertical profile of zonal mean temperature trends for CMIP 6 ensemble mean. So this is comparing historical periods, but in why is it important to use the sorry about that. So SSP 5 8.5 is obviously business as usual scenario. Well, not obviously if you don't know. Shared socioeconomic pathways 5. There are 1, 2, 3, 4, 5 which assume different things about how societies will respond in terms of renewable energy, regional conflicts, their choices for economic growth, and so on and so forth. And 8.5 is the resulting net imbalance in terms of radiative forcing the top of the atmosphere. So you can see that there are seasonal dependencies. So models are doing well in terms of winter being the maximum period, maximum season of amplification. So that's the trend being maximum there, which is consistent. So they are taking the details of the northern part here. Okay, so this is the Arctic amplification and contemporary climate models. Zonal mean Arctic amplification factor, so ratio of zonal average to global mean surface temperature average. So this is for RCP 8.5, so that's from the previous version of the models, and this is CMIP 6 SSP 5 8.5. The two scenarios approximately correspond to each other, but the models are different in many ways, and yet they produce answers that are quite similar. So can you really see any difference between them? Maybe the spread is larger here and larger here than here, but how to interpret that? This is for the long-term 2080 to 2100 average, and the period, the changes from 2015 to 2025 period to 2080 to 2100 period. Basically, the models have trouble doing this, even though they do the patterns reasonably well. There is a big problem in terms of how they do in the Eastern Pacific, which is very critical. Lots of nice papers on that from Richard Seeger and so on that you can look up. But here, just to remember that models do the Arctic amplification, they do the seasonality of the Arctic amplification in terms of maximum trends in the winter. But obviously always important to understand whether the models are doing all these things with the local feedbacks and remote forcings the same way as the real world is doing. That's very tricky. So what they do is to look at the feedbacks with the diagnostic framework, so everybody follows the same protocols to understand. So these are the diagnostic this is the diagnosis framework. Each has a strength and weakness, and there are papers on it that I won't go into. So you look at global and regional top of the atmosphere or surface energy budget decomposition, as we did here in terms of fluxes, and coupled feedback response analysis method, that's 3D analysis of feedback contributions required in terms of strength of the diagnosis, results process contributions to vertical warming profile, mechanism denial. So basically you do null hypothesis testing, idealized forcing, so sensitivity experiments to see kind of an attribution study, sea ice forcing, so that you can test the importance of sea ice for Arctic warming, and neural networks, which is an AI approach to capture non-linear feedbacks either due to large perturbation or coupling effects, or for example cloud masking of albedo and water vapor feedbacks. These are kind of details that I won't go into, but essentially there is taking model outputs and doing AI to understand the various feedbacks, or doing sensitivity studies, or assuming a hypothesis of which mechanism, like cloud radiative feedbacks, water vapor feedbacks, ice albedo feedbacks, and then do denial tests for attribution. Okay, so simple models that this paper then kind of looks at, very complicated figures with all kinds of terms. So this is summer with normal ice cover and the atmospheric profile, summer with low sea ice cover. So you can see how the various heat budgets at the surface work. So here is ocean warming. Sea ice obviously does very different things in terms of albedo and also long wave, and there are regional dependencies. If you have melt ponds, you have a very different albedo feedback compared to where there is snow or there is bare ice. Okay, I'm being very brief, but you also have exchange with the water at the bottom, whereas if you have low sea ice cover, then you change everything. Heat penetration is deeper, then you begin to create differences in the bottom interactions as well as top interactions, and you can see there is lapse rate changes as well, which has all kinds of feedbacks in the atmospheric dynamics also. This is for winter with normal sea ice cover. You can see the profile, how much it changes if you have low sea ice cover in the winter. Okay, so downwelling and upwelling, long wave radiations become important here. Long wave and sensible heat fluxes become very important in the winter, and you have obviously changes in the lapse rates in the atmosphere as well. Okay, so there are various terms that you can see. Do I need to read anything specific? Oceanic heat flux is this one. Sea ice flux is the FC that we're talking about, and which exists only when you have sea ice, obviously. What else is? Yeah, so that's very schematic, so I am also being very brief. This is for modulation of surface energy fluxes by sea ice. This is for dominant Arctic cloud responses to warming during summer and non-summer months. So if you have cooler Arctic in the summer, then you have certain albedo from the clouds, and you have again lapse rates and lots of cloud condensation nuclei and downwelling long wave radiation, and how bare ice and snow respond versus regions with melt ponds when you have a lot of sea ice. But you have warmer Arctic summer, then you have removed a lot of the ice cover, you warm the ocean. You also change the transport or the heat transport in the ocean, which is very critical, as we will see in a minute. So sensible and long wave, sensible and latent heat fluxes. You can obviously have lots of evaporation, waves, and sea salt and cloud condensation can change quite a bit, and you have changes in lapse rate as well. Okay. Are these all quantifiable? Well, this is a schematic, so obviously you want to find diagnosis framework to diagnose these things, and depending on how well the models are doing. Remember, models will have a bias in ocean circulation, in sea ice, in atmospheric circulation, in the energy budgets, in the snowfall rates, precipitation rates, ice extents, all kinds of things. But you want to just to see in each model how all these feedbacks are working. This is the cooler Arctic in the non-summer, so you have more snow content or frozen content in the clouds, and you have different albedos. You can see the albedo is stronger here than here, and you have downwelling long wave radiation being much stronger than here, and penetration of short wave much stronger here as well, and you can see the lapse rates are different as well. This is the warmer Arctic during non-summer. Again, many details there in terms of how much the ocean will open up compared to the summer season and what it will mean for these interactions. Little piece of ocean that's warm will have tremendous amount of heat loss from the ocean to the atmosphere, because sea ice is a very good insulator. So you will obviously change the sensible and latent heat flux tremendously when you have open ocean. Okay, so you can see here tremendous loss of sensible and latent heat when you have non-summer months and colder atmosphere, warmer ocean, right? So lots of losses. This is the surface energy budget response by surface type. So this is from CMIP 6 SSP 8.5 ensemble mean surface energy budget. I won't go into the details here, but these are surface types similar to the previous figure here. I skipped that figure actually, doesn't matter. So polar winter going into October, November, December, January, February surface fluxes, you can see what dominates. So long wave, latent, sensible, and net here. So you have long wave, upwelling and downwelling being tremendous with a small difference between them, and similar amounts in sensible and latent heat fluxes. This is for ocean. Obviously you have larger difference in the downwelling and upwelling, but you have huge amount of sensible. As I mentioned, if you expose the ocean to cold atmosphere, it's going to lose tremendous amount of sensible heat. And if you have sea ice cover, then you change all those things. But you can see here you change the long wave upwelling and downwelling quite a bit because of this, because the temperature. Remember, long wave is sigma t to the fourth, right? So that's what gives you. So there is also a change in the atmosphere. So downwelling and upwelling long wave are both changing. And similarly here, this is for polar winter, and these are the same surfaces, but this is for the longer period compared to what we have between 2015 and 2035 compared to 2080 to 2100 period. Anyway, just remember that these feedbacks are complicated. There are many components. It's not just ice albedo feedback, as we keep saying, because that's easier to say, but that's hardly the total story. This schematic illustrates how moisture transport from lower latitudes into the Arctic contributes to the water vapor triple effect, so warming from condensation, the greenhouse effects of moisture, and then also clouds. Water vapor is a strong greenhouse gas, and it can condense and cause heating, and can form clouds and change the albedo feedback and precipitation. So water vapor transport from both sides shown here, and you have various processes then kicking off: local Arctic warming, greenhouse effect of clouds, and greenhouse effect of the water vapor itself, heat release at condensation levels, and local Arctic feedbacks induced remotely because of this water transport. So these are the remote effects in yellowish colors, and local effects induced by the remote supply of water vapor. So always important to see how local feedbacks begin to respond to remote forcing, whether they will amplify the remote forcing or damp the remote forcing, and how that leads to Arctic amplification itself, right? This is the ocean heat transport and Arctic warming. This is the correlation between the trend of average SST over 60 to 90 north during 2015 to 2100, and northward ocean heat transport averaged over 2015 to 2100 across different latitudes in the Atlantic basin from 18 CMIP6 models under SSP 5 8.5 scenario 4A. For each model only something is done. So correlation coefficient is very high as you get into the Arctic Circle between the average SST, between trend of average SST and ocean heat transport. So this is something we mentioned before, that Arctic may be becoming Atlanticized in some sectors, because the changes in the meridional circulation is such that there is more of the Atlantic waters coming into the Arctic, some parts of the Arctic. This is the SST trend versus Atlantic plus Arctic heat transport in petawatts. So that's from the various models, and they all seem to agree that as SST warming happens, there is a higher heat transport into the ocean. Okay, we're getting close. Illustration of the fundamental processes generating Arctic amplification in the conceptual model. Okay, let's start here. C1, positive local feedback. So sea ice, clouds, and water vapor amplify initial forcing more strongly in the Arctic than anywhere else. Second one, strong stable atmospheric stratification restricts corrective exchange with the free troposphere and focuses warming near the surface, which explains the bottom heavy warming in the atmosphere. So again, you have here atmospheric circulation, water vapor, and atmospheric temperature profile, bottom heavy, as we said. C3 says seasonal energy transfer from summer to fall and winter by ocean heat storage in combination with sea ice loss, exposing the larger thermal inertia of the ocean that promotes fall and winter warming maximum. So why does winter warm the maximum? Ocean transport has a role to play as well. Sensible and latent heat fluxes are of course important. Ocean heat transport, ocean mixed layer budget is very critical because that's what determines the SST and the exchange with the deeper ocean, and how rapidly SST warms, how it affects the sensible heat, etc. So this is during polar night and this is during polar day. Okay, so C4 then, increased poleward latent heat transport amplifies Arctic warming through the water vapor triple effect that we mentioned, heating, greenhouse and clouds. Okay, latent heat release, that's from the water triple effect, greenhouse effect of the added moisture and cloud formation. Okay, finally C5, activation of positive local feedbacks by increased poleward latent heat transport drive additional warming. So this is latent heat transport, so moisture coming in as opposed to ocean heat transport, atmosphere heat transport, latent heat transport. Okay, so keep all these things in mind. What's the main point? Again, obviously a lot of unknowns, but observations very clearly show Arctic amplification. We want to understand in the future what happens, so we looked at some SSP 5 8.5 scenarios, and there isn't much good news. It's not going to slow down anytime soon, but obviously as mitigation goes on, we'll have to see how reductions in greenhouse gases, if we begin to hit the targets, how that will affect the Arctic amplification, right? That's a critical question. So let's leave that here for now. It's a nice paper, review paper, lots of references, lots of details. I've skipped tremendous amount of details and just made it very brief, but hopefully it's good enough introduction for you to learn what you want out of this and follow up with the paper if you want more details. Okay, see you.